Hey, this is Mary Montgomery for the Rendering and Graphics final project. I made two scenes, one that's fun and nice to look at, and one that just covers all my technical bases. So let's look at the fun scene first, since there's a little less to it. Here it is loading in, and here we go. So here we have two cute girlies enjoying a picnic in the park, while that tyranny of choice hand is circling to decide what to eat for lunch. So I modeled, UV unwrapped, and textured all these models in Maya, then exported them to Blender, making sure they were interesting multi-mesh objects. They're all using the texture color multi-light shader, so we can utilize all these cool lighting effects. Then we also have a skybox showing the park and a terrain model height map for the picnic blanket. So moving around the scene, we have our skybox. It's pretty small so that we just look like we are properly scaled in this little park moment. And then in here we have all of our things. So if we freeze frame for a second, we can see the different sort of lighting effects applied to different meshes. So for example, like the gem here has a higher specular than the matted hand or even the ring part of it. The nail we can see has some shine to it. Let's keep it moving though. We can see our lighting effects kind of on all of our objects, some shine to things. And just one more example is like the donut. So we can see that the glaze of the donut has a nice shine to it, whereas that cakey portion of the donut has a matte texture, not really much shine to it at all. So there's my little fun scene. We can see the blanket has some height map to it. Again, our skybox. So yeah, let's look at the code. So let's start with skybox. So my final updates to the skybox, and same with the terrain model, is that the constructor now takes pointers to the skybox texture and shader that we're storing in our skybox objects. We also can set the world now, just for ease of rendering. So now our skybox has our model texture, shader texture, and matrix. It operates the same as a model or a graphic object. More likely, sorry, graphic object. So yeah, that is our skybox. We have that implemented in the CPP file, where we're now taking in the texture and the shader. We're constructing our skybox with our vertices and triangles, remembering to set our UV map and our normals, which is pretty straightforward for a cube. Then we're cleaning up, setting texture, setting world, and rendering, where we set the shader to context, send the shader the texture, send it the world, and then we can render out our skybox. Next is the terrain. So same thing as I was saying. In terrain model, we're now taking in a texture and shader. We include that in our constructor now. We just have some helper methods that help us construct the actual terrain based on the image, the height map image we're taking in. So setting our shader and texture, creating our height map, setting the position, the UVs, the normals, which these normals aren't to stay. Here we actually calculate the normals based on all the 6 triangle faces that are touching each field vertice, which is what we have those helper methods for. Index buffer, setting our triangles, our helper methods, etc. Setting the texture, and then our render here, we're setting the shader the texture, and setting the terrain model to context. So next let's kind of move into shaders. So here is an HLSL file. They're all kind of acting in the same way. So our this is our texture color multi-light shader file, and we have our structs, our textures, our samplers, our structs, our constant buffers eventually. And then we have our vertex shader and pixel shader. And so the change to the pixel shader when we have to account for multiple lights is that we loop through our point light and spotlight arrays to add all of our ambient, diffuse, and specular colors from all of our lights, and then returning that light with the texture. So we access those shaders through our shader header and CPP files. This is our shader texture color multi-light header file and accompanying CPP file. So these are just methods to sort of set things for the shader, like our texture and sampler, all of our lights, our camera and world matrices, materials, and then in private we have those same structures as defined in the HLSL file, as well as the constant buffers. Looking at that associated CPP file for that shader texture multi-light class, we make sure to call the correct shader file, that HLSL file, and then all the other construction things like creating all those constant buffers and input layout. The interesting thing here is that for the point light and spotlight functions, setting those parameters, you can either specify an index or not, just because we have an array of point lights and spotlights. If you specify an index, it'll just set that particular point light. If you don't specify an index, it'll just set the 0th index to that those parameters specified, just so that these functions work, whether there's 8 lights or just 1. Setting the light parameters, we have to account for all of the lights and all of the arrays of those point lights and spotlights. And then setting the world material, setting it to context. Those shader classes now are accessed through our graphic object classes. So all of these shaders are kind of accessed the same way through these graphic object classes at this point. So these are friends of the shader classes. And then these have the ability to kind of just set those functions that were within the shader classes. These graphic objects contain a model, and they also contain a shader, texture. In this case, since we're using lighting and materials, the ambient, diffuse, specular arrays, material arrays, and then the world matrix. So we can look in the CPP file, and we are creating the graphic objects with a shader and a model. We are creating the meshes if that model has multiple meshes. If not, it just stays as a single mesh. Setting the world, setting the texture. We can either specify a mesh number or not. If we don't, then all meshes are set to the same texture. Or if there's just one mesh, it's set to the texture. If we specify a mesh num, only that mesh is set to that texture. Same goes for material. And then render it out. We render per mesh. We set the model to context and then render out whatever's needed for that particular mesh with changing the world, material, and texture for that mesh. So finally, looking at our dxapp.h file, we have all our imports, and then we are creating our shaders, our graphic objects, our models, our textures, our world matrices, and some vectors for position of lighting. And in dxapp.cpp, we initialize all our models, our shader, our graphic objects using that shader and those models. Then we set the texture materials for all of our graphic objects. That goes on for a little while. The interesting part here is that our blanket and skybox can be created all the way down here because we just created their texture, and that can be called in the constructor with their shader as well. Our skybox is using just a plain shader texture shader because it doesn't have lighting effects to it, so we create that with just the texture shader. Continuing on, then we set the world matrices for all our graphic objects. So we set the world matrix and then set the actual graphic object world. And then finally we're creating those positions for the point lights so that they can move around, initializing where to set the camera. In our update scene is where we move the lights and the hand. We're rotating everything around the y-axis pretty slowly. And then in our draw scene, we're setting our shader to context, setting the cam matrices, then setting all the lights. We have our directional light, and then we have all of our little point lights over each of the foods, which use those changing positions. Setting and setting the eye position, and then we can just render out all of our models, all of our graphic objects, as well as the blanket, which is our terrain map, and then our skybox after we set the correct shader to context and send the cam matrices. So that was our first scene. As we can see, the memory tracking passed. So let's move on to our technical scene. Alright, now let's play my technical scene. Awesome. So here we have nearly all of our shaders and models on display. On the far left, we have our basic color shader, which has no lighting effects. To the right of it, we have our basic textures, which also have no lighting effects. In the middle, we have our color light shader, which we can see has multiple lights and lighting effects. To the right of that, we have our texture color light shader, which only allows one lighting effect of each light type. And finally, all the way to the right, we have our texture color multi-light shader, which allows for as many lights and lighting effects as we specify. We also have our flat plane in the back and our terrain map. The flat plane is the color light shader, same as this middle row of graphics objects. And right now we have a fog effect turned off. So just moving in on our scene, we can see all the colors, the reflections. We can look on the other side of things. We get different lighting effects in the back here. But now let's see it with the fog effect. So the fog is only affecting our color multi-light objects, which is the plane and that middle row of graphics objects. The fog is hot pink. So from this distance, that background just looks like it is hot pink, but zooming in on it, we can see that it is in fact still yellow. It's just being totally covered by fog. And same with the models. When we zoom out more and more, they also get fully overtaken by the fog. But as we saw with that turned off, the scene looks totally normal. So let's get into the code. In general, for the shaders, I remade the color light shader and the color light texture shader to include multiple light sources. I did not add light sources to the shaders that didn't previously include light, like the texture shader and the color shader, as we saw. I also added the fog effect to a few of the shaders, so let's take a look at the shader color multi-light shader that we are using for the fog in that scene. So here we have that color multi-light HLSL file. It's all the same. We have our materials and all of our lighting effects, but also in constant buffers we now have our fog buffer, which has a start, a range, a color, and a boolean to tell if the fog is showing or not. And the fog is implemented in the pixel shader, so all of our functions sort of stay the same. In our pixel shader, we now loop through our point lights and our spotlight arrays to make sure we're getting all of our lighting effects. And then we also have the fog. This is mainly taken from the demo you gave to us, but it also implements something that the textbook did, which was lerp the color instead. So we are figuring out the fog percent and lerping that with the already lit color as well as the fog color, and then just returning that lit color. Since we don't have a texture to also apply to the pixel shader, it is just this color and fog lighting effect. So next is our shader. We have our shader color multi-light, which is how we access that HLSL file. It's the same idea for all of our shader classes, accessing those HLSL files, but here's the one specifically for the color multi-light. So we have our constructors and setting it to context. Then we also have all of our light parameters, setting, Then the new thing is also sending the fog. I kind of went over all of these in the fun demo, but we have the indexed point light parameters and the non-indexed point light parameters. Same goes for spotlight, so we can specify a particular light to set the parameters of or not. And then what was added here is this fog constant buffer. It's a structure, it's also the constant buffer, stores the fog start, fog range, fog color, and a boolean if the fog is showing. It defaults to false, so if we don't set any fog, this is false, and within the shader, we see that we only add the fog effect if the fog is showing. So if this fog showing equals true. So when it equals false, by default, none of this fog lighting effects will be added. And then this is implemented in the CPP file. First in our constructor, after the input layout, we make all the buffers. So we need to make a fog buffer, which is set here. Oh, I forgot to release and delete that constant buffer, so let's add that here. Okay, setting the matrices, the lights, again, with the index or without. Setting all of our light parameters, sending them. And then sending the fog parameters, we can specify a start, range, and color input. We set our fog to that input, set the fog showing to true, and then update that sub-resource to send it to our HLSL shader file. And we also needed to add that constant buffer in our set to context. So that is how we added fog to shaders. It was the same across all shader files that added fog to them. And then quickly, the graphic light .h. So this is, nothing changed in the graphics objects to implement fog. That was all taken care of in the shader, but now just this shader includes that fog effect. So these models that are created with this are affected by that fog effect if one is there. Very similar to the graphic object we looked at in the last video. This one just contains colors and multiple lights. So it's created the same way with our model and our shader, setting the different meshes with the material arrays if different meshes exist, etc. Set material, you can either specify a mesh number or not to set a particular mesh number or set them all, and then rendering it out, set the model to context and render out the world and material. Now we don't have to send a texture and sampler, just the world and material, then render the mesh. Okay. The last thing to show are the models themselves. The full creation of a model is split across a few classes. We have the model class, the model tools, as well as the mesh separator class. My code is only in the model and model tools classes, so we'll take a look at those. Over here in model, we have the creation of the standard vertex struct, which we use all throughout the vertex creation. We have a position, the UV, normal, color, and a mesh num. There's a hacky trick in mesh separator that kind of expands on this standard vertex structure and structures it a bit differently, but this is what we created. We have all our different set functions that take different parameters based on what exactly we need to set per vertex. We also have the triangle by index structure, which is how we set up our triangles for our index buffer, as well as just the model class itself, everything that's included in it, our triangle lists, our standard vertex lists, the number of verts, the number of triangles, the meshes that we get from our mesh separator class, our GPU connections, etc. In public, the most important thing here is our pre-made models. The models we've created are the unit box with repeated texture, unit box with 6 different face textures, unit pyramid with repeated textures, unit sphere, and I also have a unit textured sphere. Then we have our, basic destructors, set to context render, render per mesh, get mesh count, valid mesh number. In model.cpp, the most important thing for us to look at here are what I implemented in this switch function within our model constructor, which is how we create the models themselves using our model tools class. So in each of these cases, whichever model we're creating calls the model tools class to create that structure, or that, model itself. So we have a call to all of our different models that we described in our enum pre-made models. And then just the rest of this class. And then model tools. So in this class, we're just calling those create methods for whichever model we are creating. And then I also have a function that's just a helper function for creating the pyramid that is not sort of within the model tools class, but it does need to be defined. And so within our model tools class, we create a unit box. So all of these are pretty similar. We are setting, first creating the number of vertices we need, putting them in a standard vertex array, and then creating the number of triangles we need and creating that triangle array. Then we create our vertex, the set function of the x, y, and z position, the uv, and the normal x, y, z. And then we create our triangles by winding those in the correct counterclockwise order. So the cubes are pretty straightforward. The repeated texture, these are just differences in setting up the UVs based on where in the texture we need. So for a repeated texture, the UVs, we can just use the full 0, 1 square for each face of the cube. But for the 6 face texture, we need to split up that 1, 1, 1 UV into its own little boxes to texture each face differently from that same 1 by 1 UV coordinate. And then just adding on the normals as well. Create unit pyramid. So we duplicate the vertices for all of these. All of these models, we duplicate the vertices for differing normals. So for the pyramids, the vertex normal is equal to the normal of the face, which is found using the 3 vertices of that face, which is where we get that helper function I made, that normalized pyramid sides, which just finds the normal of that triangular face, sets the normal, sets the UV, etc. Pyramid repeated texture. Same sort of thing, but just changing the UVs here. There's our little normalized pyramid sides helper function. And then our create unit sphere. So this creates a sphere of radius 1 with the V-slice as the vertical bands and H-slice as the horizontal bands. So there's a ton of comments here. It took me a while to figure this out, of drawing it and kind of making notes for myself, but this unit sphere does not duplicate vertices, and the UVs aren't correctly mapped in this one, but it does create that sphere. However, I do have the create unit texture sphere, which does duplicate the vertices and correctly maps a UV texture to it, as we saw in the final scene. So let's go through this one real quick. So we create our number of vertices, which is, there's V-slice verts for the top and bottom rows, then V-slice plus 1 verts for all the middle rows. So that's how we get the number of vertices, make our standard vertex array. The triangles are, there's V-slice triangles for the top and bottom rows, and V-slice times 2 for all the middle rows, because all the middle rows are making quads that need to be split. Each quad is split into 2 triangles. So that's how we get the triangle array. Our vertical increment and our horizontal increment are figured out by diameter. So horizontal, we're going all the way around the circle, so we need to take that full 2 pi diameter and divide it by the horizontal slice number. And vertical, we're only taking half of that diameter, so pi divided by the number of vertical slices. Remember, the normals are just the points themselves, so that's pretty straightforward. I have a lot of variables here to help me keep track of everything in there. What index we're on, for example, the x, y, and z point, normalized vector, the current u position, the current v position, and then the incremental u distance and the incremental v distance for the UV maps based on how many slices there are vertically and horizontally. And then we kind of just go by row by row, column by column through the sphere. The top and bottom rows both just map to the respective 0, 1, 0 or 1 or 0, negative 1, 0 positions. So we have conditionals for that. But the top and bottom rows don't have that extra vertice. When we're looking at that UV map, the top and bottom rows only have our triangles, not that extra vertice at the end there. So then the top and bottoms are just that 0, 1, 0. Normalize it, set the current u, current v. If we're not at the top and bottom rows, we need to figure out our position in space using cosine and sine for the x, y, and z. Normalize that x, y, and z, and then set the position. The norm is just that normalized, and the current u length, current v height. We increment the u every time we go to a new vertice, and then every time we finish each row and we go down to the next, we increment the v height as well. So then we make the triangles. So we're going through, again, the horizontal and the vertical. So I have 3 separate conditions to construct the triangles of the sphere. We start at the top of the sphere, create those triangles, get the correct winding. I have a lot of diagrams in the one above, but it's kind of a mess with comments. Create the top triangles, create the bottom triangles, and create those center quad triangles. And that is the full creation of all those model tools, remembering to add those normals, and I colored all the vertices white just because. And the final thing to look at is our DX app, now that all the models have been created in code. So we create all of our shaders, lots of different shaders, create a graphic object for each shader. So we have our multiple graphic objects per shader, so we need to create a graphic object for each of those different models. Texture, the multiple lights, the textured light, the texture color multiple lights. Create a model for each graphic object, so we have our unit box repeated texture, unit box 6 texture, the unit sphere, the unit textured sphere, unit pyramid, repeated texture, and our hot dog model. We also need to create our terrain, flat plane, skybox, and then textures for all the models, as well as matrices for the worlds of all those models. And then I also have moving lights, so I need those vectors of those light positions as well, so I can move them in our update function, looking at dxapp.cpp. Finally, let's go to the top here. In our initializer, we initialize all of our shaders, we create all of our models, and then we create our graphic objects with our models for each shader. So we have our color shader, graphic objects. Here we're using the unit sphere and unit texture sphere. This is the only place we use that unit sphere. Everywhere else is using that unit textured sphere. So for our textures, same thing, using all those models with the shader texture shader. For the light, all of our models with that color multi-light shader. All of our models with our color light texture shader, and all of our models with our texture color multiple light shader. Next is setting the textures and materials for all graphic objects. So for the color, we just need to set the color, and we can specify mesh numbers. So the hot dog model has 4 meshes, so we can specify those colors. So with all of these functions, all of these set functions, I'll be utilizing the default without mesh number as well as the mesh number specified versions. So for texture, we create all of our textures and then set the texture. This is default. This is with the mesh num specified. For the lighting, we set the material. This is just default. This is with the mesh number specified. The texture light graphic object, we're setting the textures, setting the texture default, setting the material default. Then with the hot dog, we can create our textures, set texture with that mesh num specified, and set material with the mesh num specified. Same here with the texture color multiple lights. Same thing of just creating that texture, setting it, setting the material. These are all the default, and then here we specify the mesh num. Finally, we have the terrain, which we saw in the fun demo as well. Create the texture for it, and then set the terrain, create the terrain model using that texture and the shader that we'll be utilizing, which in this case is the texture color multi-light shader. And then our flat plane is just the flat plane. I didn't really edit the flat plane class. I took out my skybox just because I didn't like the way it looked. Finally, we're creating the world matrices for all of our graphic objects. So these are all just setting the worlds of the graphic objects. Pretty straightforward there. The plane is for our flat plane, setting that world as well. And then we have our vectors of the light positions, create those so we can move them in our update scene. Here we're rotating them around the z-axis this time, so it's shining on, like facing the objects. We also set the position of the camera to view our scene better. And finally, our draw scene. We set the shader and render the objects every time. So set the color shader, send the cam matrices, render all those color graphic objects. Set the texture shader, send the camera matrices, render all the texture objects. Multiple light colored objects, this is where we added the fog. So for these ones with lights, we set to context, send camera matrices, and then send all the light parameters that we're using. So this one has 3 lights, a directional and 2-point lights. Send the eye position, send the world and materials, render the plane. The world and materials is mainly for this plane render, and then everything else just renders itself through the graphic object class. The color light texture objects, set to context, send the cam matrices, set the lights, send the lights, render out those textured light colored objects that only take 1 light. And finally, our color textured and multiply lit objects. Set to context, send the cam matrices, set all the lights. This one has a directional and 3-point lights. Send the eye position, and then render out our texture color multi-light graphic objects and our terrain. And then we present. So looking at this scene one more time to see all of that put together. So looking once more at our scene, we see everything that we were just describing, all of our models. In the color models, this is the sphere that has no texture mapped to it. It's just the non-duplicated vertices. All of these have the texture mapped to it clearly. We have our 6-faced textured cubes that have things like the dice texture on them and this like alignment sort of texture. The crate repeated texture cubes that just repeat the same 1-1 UV on every face. Our alignment test pyramids that have a repeated texture on every face. And finally our hot dogs that have the different meshes or different textures with different lighting effects. So yeah, those are the technicalities of my scenes. I hope you enjoyed. Oh, also, lots of things, but memory tracking passed.